For 1800 years, human income did not increase. A farm laborer in Roman Gaul, a plowman in medieval Burgundy, a weaver in a Tudor English village. Different centuries, different languages, roughly the same money. Around $400 a year in today's terms, which bought enough food and a decent harvest, a roof, and nothing left over. Go back further, and the number holds. Another 5,000 years of it, all the way to the first seed planted on purpose. Empires rose and burned, cities were built and sacked, and every surplus the population produced was eaten by the extra mouths that produced it. A man alive in London in 1600 earned no more than a man alive in Mesopotamia 4,000 years before him. 7,000 years. No growth. Then, around the turn of the 19th century, it breaks, and everything you own is on the far side of it. Your house, your car, the food in your fridge, the fact that you are watching this instead of bent over a field somewhere. Economists have argued for a century about what caused it. Cheap coal, colonies, high wages, property rights, Protestantism, if you go back far enough into the older literature. Every one of those answers explains why somebody would want a machine. Not one of them explains how anybody managed to build one. Because underneath the whole thing sits a problem that sounds like a riddle. To cut an accurate screw on a lathe, you need a lathe that already contains an accurate screw. The lead screw drives the carriage carries the tool, and whatever error lives in the first screw is copied faithfully into the second, and into every screw made after it, forever. So where does the first one come from? Nobody could answer that. Not the Greeks, not the Romans, not the clockmakers of Augsburg, or the gunsmiths of Saint-Étienne. Accuracy lived in a man's hands and died with him. Then, inside the working life of one Englishman born above a storekeeper's quarters at the Woolwich Arsenal, it was solved, not worked around. Solved. That break in the line is what solving it looks like. This is Trade Archive, where we follow the tools rather than the tycoons. Jacques de Vaucanson was born in Grenoble in 1709, the 10th child of a glovemaker, into the kind of poverty where a clever boy's options run to the church or the trades. He took the church, joining the order of the Minims, then spent his life on something the church had not asked for. He built automata, clockwork figures so intricate that the aristocracy of Europe paid extraordinary sums to look at them. In 1738, he unveiled a life-sized shepherd playing a transverse flute. Bellows drove air through artificial lips, and the fingers moved over the holes correctly for 12 separate tunes. A tambourine player followed. Then, in May of 1739, came the machine that made him a household name across Europe. The canard digerateur, the digesting duck. It was a gilded copper bird on a plinth, each wing reported to contain over 400 moving parts. It craned its neck, drank water, took grain from an open palm, and swallowed it. And then, some minutes later, in front of a paying audience, it deposited a quantity of digested matter onto a silver plate. Voltaire wrote that without Vaucanson's duck, you would have nothing to remind you of the glory of France. The duck was a fraud. The food went into a compartment in the neck and stayed there. What appeared on the silver plate was breadcrumb, dyed green, loaded in beforehand, and released at the correct moment. Christian Friedrich Nicolai reported the deception in 1783, and the magician Robert Houdin confirmed it on examination in 1844, remarking that it was a piece of artifice he would happily have used in one of his own tricks. So the most celebrated mechanical achievement of the French Enlightenment was a magic trick, while the same man's real contribution sat in a workshop, unregarded, and stayed that way for the better part of a century. In 1741, Cardinal Fleury made Vaucanson Inspector of Silk Manufactures. This was not a ceremonial post. Lyon was the center of the French silk trade, and the trade was in trouble, undercut by Italian and English competition. Vaucanson spent 2 years traveling northern Italy and southern France, taking machinery apart and putting it back together. Reels, bobbins, looms, mangles. He came back with a plan to rationalize the whole industry under merchant control, and the silk workers of Lyon understood what that meant for them. They pelted him with stones in the street. Public punishments were decreed and made no difference. In 1744, the trade rose over a demand to raise piece rates from 2 sous to 4 in what became known as the Revolt of the 2 sous. It was crushed, 3 strikers were hanged, and the piecework scales abolished outright. That is the part the museum plaques leave off. He was not a whimsical clockwork eccentric. He was a state official imposing industrial discipline on a workforce that fought him for it, and won, at a price paid by other men. One of the problems he was trying to solve was the calendar rolls. Silk was passed between heavy copper rollers under pressure to imprint the watered moire pattern fashionable at the time, and the pattern is only as good as the rollers, which have to be dead parallel and truly cylindrical along their length. No lathe in France could turn a copper roll of that size to that standard. The wooden machines flexed, the handheld tools wandered, and the results were unusable. So he built a machine that could. The lathe that sits today in the Musée des Arts et Métiers in Paris, catalogued as inventory number 16, is built entirely of metal. 2 polished wrought iron bars of square section, set at 45 degrees so their corners present a V, form the guideways, bolted through brass plates into a wrought iron space frame. A brass carriage rides those V-ways, traversed along the work by a fine-pitch lead screw turned with a removable hand crank. The cutting tool is no longer in a man's hands. It is clamped in a slide and advanced by a screw, in controlled increments, repeatably. There is no true tailstock. The work runs between a pair of dead centers. It cannot cut a screw thread. It was built to turn copper rolls up to about a meter long, and it did that job. Look closely, and you find match marks stamped into the components, the fitter's private code telling him which piece belongs against which. Even here, the old world of hand-fitting is written on the metal. The museum's own curatorial note calls it revolutionary and precursory, and says Vaucanson defined the principles of the lathe. You will hear this machine called the first modern lathe, the mother of all machine tools, the object that started the Industrial Revolution. That claim does not survive contact with the literature. Start with the date. The museum's website says 1751, and its own printed booklet says 1750. Fryer and Marshall, in Technology and Culture in 1979, put it at 1760. Derry and Williams place it around 1768 and leave it out of their standard history altogether. Rolt captions it 1775. The institution that owns the machine cannot agree with itself to within a year. Then there is influence, which matters more. Robert Woodbury, whose History of the Lathe to 1850 remains the reference work, dates the birth of the modern industrial metal-cutting lathe to around 1800, not 1751. The consensus among people who have traced the lineage is blunt. Vaucanson's lathe and the comparable machine Senot built in 1795 remained practically unknown. They influenced nobody, so the honest verdict is harder than the legend. He built a genuinely early all-metal industrial slide lathe, decades ahead of what surrounded it, in a country with every advantage. And France did nothing with it. He left his machinery to the crown, and it became one of the founding seeds of the institution that now houses the lathe. The machine sat in Paris while the problem it pointed at went unsolved. The answer came from somewhere else entirely, out of a cannon foundry in Shropshire and a lockmaker's shop in London. John Wilkinson was an ironmaster, not a philosopher of precision. He ran the Bersham Works near Wrexham and sold cannon, and in 1774 he took out British patent number 1063 for a new method of casting and boring iron guns. The old way was to cast a gun hollow around a core and hope the core stayed centered. It never quite did. Wilkinson cast the barrel solid and bored it out, and made one change that decided everything. Instead of hanging the boring bar from one end like a cantilever, where it deflects and follows whatever error is already in the hole, he ran the bar right through the workpiece and supported it at both ends. A supported bar does not wander. It cuts where you point it. That machine has a fair claim to being the first true machine tool in the world. Meanwhile, James Watt was failing. He had a steam engine design better than anything in existence and could not get it to work because the cylinders available to him leaked. No foundry could bore a large bore accurately, so Watt was reduced to hammered iron cylinders that were visibly out of round, steam escaping past the piston on every stroke. An engine that leaks its working fluid is an expensive way to warm a shed. Wilkinson bored him a cylinder. In April of 1776, Watt wrote to John Smeaton that Wilkinson had improved the art of boring so far that he could promise a 72-inch cylinder not further from absolute truth than the thickness of a thin sixpence at the worst part. From Wilkinson's own shop came a similar boast, that they had bored several cylinders that did not err by the thickness of an old shilling in any part. A sixpence is about a 16th of an inch. On a cylinder 6 feet across, that is not impressive by any modern standard. As the difference between an engine that runs and one that does not, it was worth a fortune. Wilkinson got an exclusive contract to bore cylinders for Boulton and Watt, and the Industrial Revolution got its prime mover. But notice what that machine could not do. It could not cut a screw, hold a small part to a fine dimension, or make another machine tool better than itself. The boring mill was a magnificent dead end in the same way the Paris lathe was. It solved a problem instead of a class of problems. Henry Maudslay solved the class of problems. He was born at Woolwich in August of 1771. His father had been a wheelwright in the Royal Artillery, wounded out of service and given a storekeeper's job at the arsenal, and Henry started there as a boy filling cartridges. He moved to the smithy. By 18, he had a reputation as the finest young hand in the district, and in 1789 he went to work for Joseph Bramah in London. Bramah had just patented a lock, built around sliders that had to be depressed to precisely different depths before the barrel would turn, and it was unmanufacturable by the methods of 1789. Maudslay spent his years there building the machines that made it possible, and Bramah put the finished article in his Piccadilly shop window with a standing offer of 200 guineas to anyone who could pick it. It stood unpicked for 67 years. When Maudslay asked for a raise, Bramah refused. So he left, took premises of his own, and hung a large brass screw in his shop window. Not a lock, not a machine, a screw. It was the only advertisement he thought he needed, and every mechanic in London who walked past it understood what was being claimed. What Maudslay had worked out is the hinge of this entire story. Start with the problem of originating a thread when you have no accurate thread to copy. One method he used was almost embarrassingly simple. Take a plain cylindrical rod, wrap a thin, inclined knife blade halfway around it, set at the angle corresponding to the pitch you want. Turn the rod and the knife scores a helical line into the surface. That line is not a usable thread. It is a guide, generated purely from geometry, from an angle and a diameter, rather than copied from any existing screw. Deepen that helix by hand into a thread on a soft blank, and you have a crude lead screw. It does not need to be accurate. It only needs to be better than nothing. Now fit that soft screw into a lathe, use it to drive a carriage, and cut a new screw in a harder material. This is where the arithmetic turns in your favor, because the errors in a lead screw do not all run the same direction. Some threads come out marginally long, some marginally short, and as the carriage traverses, they partially cancel. The tool rides an average of the errors rather than any one of them. The second screw comes out better than the first screw that guided it. Fit the second screw into the machine and cut a third. Maudslay built a dedicated device for exactly this, a screw-originating machine that cut only soft metal, whose entire output was a better screw for a better lathe. Each generation is the parent of something more accurate than itself. That is the bootstrap, and it is the answer to the riddle we opened with. Precision is not found or inherited. It is compounded, one generation at a time, by a process that averages error out faster than it accumulates. Maudslay then made the second move, which turned a clever trick into an industry. His early lathes needed a separate lead screw for every pitch, since the screw driving the carriage had the same threads per inch as the one being cut. Within a year, he abandoned that. He built one lead screw, as accurate as he could manage, and geared it to the spindle through a train of interchangeable wheels. Change the gears, and you change the ratio between spindle rotation and carriage travel, and one machine will cut any pitch you ask for. We still call them change gears. On a manual lathe in any jobbing shop in the world, that is still how it is done. The lathe he built around 1800, now in the Science Museum in London, is a plain thing on two parallel triangular bars. A slide rest rides both, carrying a tool holder with a screw feed and a micrometer dial to set depth of cut. The lead screw runs between the bars. The change wheels are missing now. It was turned by hand. One more correction, because the trade deserves it. You will read everywhere that Maudslay invented the slide rest. He did not. That claim traces to an ambiguous 1841 pamphlet by his pupil James Nasmyth, and Jesse Ramsden had combined lead screw, slide rest, and change gears around 1775. What Maudslay did was harder. He assembled the existing elements into a rigid, coherent, commercially available machine and put it into the hands of everyone. And he measured. On a bench in his shop stood an instrument his men called the Lord Chancellor, because it was the final court of appeal in any dispute about a dimension. A bench micrometer reading to 1/10,000th of an inch. When two of his workmen disagreed about a size, they did not argue. They went to the Lord Chancellor, and the Lord Chancellor ruled. The bootstrap is not confined to screws. 3 fundamental forms generate themselves out of nothing, and between them they account for almost everything a machine shop does. Roundness comes free on a lathe. Hold a tool at a fixed distance from a rotating axis, and, whatever shape the blank started as, the tool sweeps a circle. High spots get cut away on every revolution. The machine needs no roundmaster to copy. It produces roundness out of the geometry of rotation itself. Straightness comes from constraint. A tool made to travel along a way is straight to the extent the way is, and a straight line can also be generated as the intersection of two flat planes, which pushes the problem back a step, which leaves flatness, and flatness is the beautiful one. How do you make a flat surface with no flat surface to check it against? Comparing two plates tells you nothing, because a convex plate and a matching concave plate sit together perfectly and both are wrong. Two surfaces can agree and both be curved. 3 cannot. Take 3 cast iron plates. Blue the first, rub it against the second, scrape away the high spots the ink has marked. Now the first against the third. Now the second against the third. Keep rotating the pairings. Any curvature that let 2 of them agree is contradicted by the third, and no shape other than a true plane satisfies all 3 pairings at once. Given enough patience, and it takes an enormous amount, the plates converge on a flatness that existed nowhere before you started. Joseph Whitworth, one of Maudslay's men, made this practical in the 1830s. Earlier attempts used grinding and polishing, which follow and generalize the errors already present. Whitworth used a hand scraper and engineer's blue, Prussian blue in a non-drying oil, which shows exactly which points are carrying load, so you remove those and nothing else. He published the method in 1840. His plates were ribbed cast iron, left outdoors a year before machining, because iron that has not settled will move after you have finished making it true. That is the datum. Every flat surface in a modern factory descends from 3 plates, a scraper, and a tin of blue. Whitworth kept going. In 1851, at the Great Exhibition in the Crystal Palace, he showed a measuring machine that could detect a difference of 1/millionth of an inch, a figure he explained as roughly what you get by dividing a sheet of thin French writing paper into 4,000 thicknesses. A millionth of an inch was the resolution of a comparator under laboratory conditions, not a tolerance anybody held on a production floor. His workshop micrometer of the 1840s read to a 10,000th. The direction of travel is what matters. In 1776, Watt was delighted by a 1/16 of an inch, and in 1830, a skilled mechanic still worked to about that same 1/16. By 1840, a 10,000th was practical, and within one further generation, the shop yardstick had moved to a 1/10 of a 1,000th. His other contribution was different in kind and is often folded into the first, which is a mistake. In 1841, he proposed a national standard for screw threads, a fixed 55-degree angle, a defined pitch for every diameter, depth, and radius, specified as fractions of the pitch. British Standard Whitworth. Precision and standardization are separate goods. Precision means your part is close to the dimension you intended. Standardization means your part and a part made 300 miles away by men you have never met will thread together. The railways adopted it first, each line having settled on its own threads. Sir John Penn built 90 identical marine engines in 90 days for the Royal Navy's Crimean gunboats, which is not a feat of craftsmanship. It is a feat of agreement. The Royal Navy proved what all of this was worth. Between 1803 and 1805, 45 machines of 22 types, designed by Mark Isambard Brunel and built by Maudslay, went into Portsmouth Dockyard to make the pulley blocks for the fleet's rigging. By 1808, they were producing 130,000 blocks a year, and the claim made for them was that 10 unskilled men working the machines could replace 110 skilled blockmakers. That was the first time anywhere that a line of all-metal machine tools was used for continuous mass production. Which brings us to the question that shaped the 20th century. If a machine can hold a dimension without a craftsman, can you make parts that fit anywhere, rather than parts that fit one particular assembly? A French gunsmith had already proved you could, and France had already thrown it away. Honoré Blanc had apprenticed at 12 and worked up through the Charleville Armory to controller of 3 arms factories, extending Gribeauval's program of standardizing French artillery. In 1785, at the Château de Vincennes, he took roughly 50 musket locks apart, scattered the components across a table, and reassembled working locks from parts picked at random. Sitting in the audience was the American ambassador to France. On the 30th of August, 1785, Thomas Jefferson wrote to John Jay, describing an improvement in the musket in which every part is made so exactly alike that what belongs to anyone may be used for everyone in the magazine. 4 years later, he wrote to Henry Knox that he had put together half a dozen locks himself from a promiscuous collection of parts, taking the first pieces that came to hand. Blanc could produce interchangeable locks at about 10% above normal cost. Then Gribeauval died, and Blanc died, and the guilds and the political opposition won. France stopped making interchangeable arms, and in time forgot it had ever known how. The idea crossed the Atlantic, and what happened to it there is one of the most successfully falsified stories in American industrial history. In 1798, Eli Whitney took a government contract for 10,000 muskets in 2 years. By 1801, he had delivered none, so he went to Washington and performed a demonstration for President Adams and Vice President Jefferson, assembling muskets from what appeared to be randomly chosen parts, and walked out with his funding extended. The order took him roughly 10 years. The demonstration was rigged. The parts had been marked in advance, so Whitney could match them back to their partners, and the swap involved dropping lock assemblies into loosely cut wooden stocks, rather than exchanging any working component. Robert Woodbury laid the case out in Technology and Culture in 1960, and Merritt Rose Smith went further, concluding that Whitney staged the demonstration with specimens prepared for the occasion and purposely deceived the government. Examination of surviving Whitney muskets confirms it. The locks are not interchangeable. The man who actually did it was John Hall, in a converted sawmill on Virginius Island at Harper's Ferry, fighting the armory superintendent for every yard of ground. Hall understood what Whitney never grasped, which is that interchangeability is not an assembly technique, it is a tolerance problem. Conventional gun lock work ran to around 0.2 of a millimeter. Hall needed 2/100ths, 10 times finer, held across thousands of parts made by ordinary men. So he built water-powered machinery running through leather belting, some of it turning above 3,000 revolutions a minute, and a system of 63 gauges, so every part was checked against a fixed standard rather than against the part it was destined to meet. In 1826, a government commission took 100 Hall rifles, stripped them, mixed the components, and reassembled them onto newly delivered stocks. Everything fitted. That is the first documented achievement of interchangeable manufacture in the United States, and it cost about $150,000 over 5 years. Hall's own summary was that one boy with these machines could outwork 10 men with files, and do it more accurately. It happened inside government armories rather than the open market for a reason. Interchangeable manufacture cost more than skilled hand-fitting, and no private customer would pay the premium. The Ordnance Department would, because a weapon repairable in the field from a box of spares is worth more to an army than a cheaper one that is not. Springfield and Harper's Ferry subsidized the transition until costs came down, and then the method spread to clocks, sewing machines, typewriters, bicycles, and eventually automobiles. The British found out in 1851. At the Great Exhibition, an American display that had started out embarrassingly sparse took a disproportionate share of the prizes, and the firearms drew the attention. Samuel Colt disassembled 10 revolvers, mixed the parts, put them back together, and lectured the Institution of Civil Engineers on how it was done. 3 years later, the Board of Ordnance resolved to equip its new armory at Enfield with American machinery. The report its committee filed in 1855 is where the phrase entered the language, the American system of manufactures. Which brings us back to the 7,000 flat years we started with. Every other technology in human history had to be built by something outside itself. Precision is the only one that is its own parent. A lathe cuts a lead screw for a better lathe, which cuts a better lead screw still. 3 plates and a scraper make a flat surface out of none. The capability compounds, generation on generation, and it has never once run backwards. Vaucanson saw a piece of it in Paris and France let it sit. Wilkinson bored a hole straight enough to hold steam. Maudslay closed the loop and trained the men who carried it everywhere. Hall proved that what one machine could hold, 10,000 parts could hold. The finished object of all that work is not in a museum. It is the phone in your hand, the bearings in your car, the bolt holding your chair together. Everyone descends, by unbroken line, from a soft metal screw that somebody cut with a knife wrapped round a rod because he had nothing better to copy. If that lineage is your kind of story, subscribe to Trade Archive. The next video is already on your screen right now. See you there.